Saxon Advanced Mathematics, Lesson 90. Students, today is, buckle in for this lesson. It's a biggie. It's an identities lesson, as you can see, and this marks a turning point in our studies of identities. Up until now, we have learned new identities, and we have just memorized them and used them pretty much as they stand. In the future, going forward from here, a lot of your work in identities will focus on taking identities that we've already studied and memorized and learning to manipulate them, move them around to create new identities that can be used. That's the way the future of your identities studies from here on out will trend. It's more about manipulating the old ones and changing their shape rather than just memorizing new ones. So what we're asking, John and I are asking of you is, rather than memorize anything, remember these processes. Remember the steps for taking familiar identities and turning them into something new. The example simply asks us to develop these identities, so we'll call it an example, but we're really just doing the work. The first one we're going to do is the double angle identity for sine. It looks like that, sine of 2a. Okay, what we're going to use to develop this identity is one that we already know. It's the sum identity for sine. We learned this fairly recently, but we know that there is an identity for this, and I'm going to squeeze it into this space. Sine A cosine B plus sine B cosine A. And sometimes I write this as cosine A, sine B. I flip the order of those. It doesn't matter. Either way is fine. If you have a preference, you can write it the way you like it, or you can just be like me and go with the flow. Now, here's the way we're going to take this and manipulate it so that it becomes a double angle identity. Instead of assuming that A and B are two different angles, right? These are our arguments, if you will. These are the degrees. What we're going to do is we're going to say, instead of adding two different things, A plus B, we're going to think of them as the same letter. We're still adding them, but it's just adding the same thing twice. So let's rewrite what that would look like. It would be sine A cosine. Now this B turns into an A, right? Because both of them are A's. And then the same thing happens over here. Sine A, cosine A. Both of these become A's, right? So one final step to simplify this. The sine of 2A, right, if we add those together, equals 2 sine A cosine A, right? Because this, that's an A, looks like an R. Sine A cosine A, sine A cosine A. We have two of them. We're adding them together. So this is our double angle identity for sine, okay? That is what we were trying to develop. One important tidbit there is only one double angle identity for sine. Spoilers, when we do cosine, this is not going to be the case, okay? So when we're finding a double angle identity for sine, there's just one answer, and it's right here. When we do the same thing with cosine on the next page, what we're going to see is that we can actually create three different styles, I would say, three different versions of the double angle identity for sine, or for cosine rather. There's only one for sine, but there are going to be three for cosine. So let's take a look at that. Okay, so this is part B of our problem, and we're finding the double angle identity for cosine. Okay, we're going to do the same thing. We're going to take the sum identity for cosine and start with that. So that's the cosine of a plus b equals sine is the opposite, right? And then sine A sine B, okay? So we have the same starting place. We use the sum identity. Now what we're going to do, just like we did last time, is said, hey, instead of having these be different, let's make them the same, A plus A. That will change all of these B's to A, so let's take a look at that. Cosine A minus sine A sine A, right? We're turning all the B's into A's. So now we can simplify this. The cosine of 2A equals cosine squared A minus sine squared A. This is the first form of the cosine double angle. As promised, there are going to be 3, but this is the first one, okay? And we're gonna work from this to develop the other 2. What we want to do now is take a look at this and go, wait a minute, cosine squared A, sine squared A, those look familiar. We have Pythagorean identities. We're going to start with cosine for the first one. We've got a Pythagorean identity that we can use. It equals 1 minus sine squared A, right? Oh, I'm sorry. This should just be a minus sign, not an equal sign. This is the equal sign, right? 1 minus sine squared A. So what we're going to do is we're going to substitute this in here and then simplify. Oops. So I'm taking this cosine of 2A and I'm substituting this in for cosine. 1 minus sine squared A, and then this, minus sine squared A. Okay, so here is where we substitute that in. We can combine these two so we get that the second form of the cosine double angle identity looks like this. Okay, now we're going back to develop the third form. We're going to go back to here, and this time what we're going to do is take the other, we're going to reshape the Pythagorean, and this time we're going to substitute it. I'm going to use blue so the color looks a little more different. Color matters, man. Now we're going to change up this part of it, and we're going to take Pythagorean, and we're going to rearrange it this time so that sine squared A is by itself. And you probably remember sine squared A equals 1 minus cosine squared A. So we're going to take this and substitute it in to the original, right? We're not using the second form. We're going back to the first form. So now this is my Pythagorean that I've got. Now I'm taking this and I'm saying the cosine of 2A equals cosine squared A minus, and now we're using this expression for sine squared A, right? That's the same. So I can substitute this in, and I'm gonna need parentheses here because look, there's a minus sign. So this is the trick of the third form, is you have to be really careful about this minus sign. This is 1 minus cosine squared A. So then let's distribute that minus sign. It'll be minus 1 and then plus cosine squared A. And now for my final version of this, I'm going to add these two cosine squared A's together, right? Just like we combined the two sine squared A's here. For our final version, we'll say that the cosine of 2A equals 2 cosine squared A minus 1. And there's our third form. And again, let me say, John and I do not want you to memorize these. What we want you to do is remember the process. To develop the double angle identities, we start with the sum identity, change both values to A, simplify, and then to develop, that's the first form, and then to develop the second and the third, we use these Pythagorean identities and substitute in so that we change it into the second form and the third form. And I always substitute this, here, where am I? Substitute this one first, substitute cosine first, because that's the easier one to plug in. When we substitute in for sine squared A, that one's a little trickier because of the way the minus sign works. So let me do this. I want to circle this and circle this. And I want to circle this and circle this. There you see the matching signs, and then this is where we substitute it in. And here's this one. Okay? So once you start substituting, substitute cosine first and then sine second. That way you'll remember, oh yeah, the third one is super tricky. These, remember, are Pythagorean identities. And same for this one. Okay, so now that little cosine one that we did before, that one seems like a pretty cute little cupcake, doesn't it? So easy, right? So sine, there's just the one form. But cosine, when we create the first form, we realize, oh, we can substitute that one, we can substitute that one, and that's how we get the second and third forms. Okay, so far so good. Now what we're gonna do is we're going to figure out how we can use these identities to create one for tangents double angle. All right, we're gonna do that in just a minute. We will come back and we will be using this one, just so you know. We're not gonna redevelop it, but we're gonna use this when we do tangent. All right, this is the first of the three. So let's go on to the second. John calls this a second example, I guess. And what we're going to develop is the double angle identity for tangent. Tangent of 2A. Now this one, we're gonna develop differently because we don't have a sum identity for tangent, right? We figured out how to do that by just putting the sine over the cosine. And that's what we're gonna do again. We're gonna put the sine double angle identity over the cosine double angle identity, the first form. That's what the 1 refers to, is we're going to use the first form. Okay, so what we can do is kind of rattle through our brains a little bit and try to remember how we did that. You can look back in your notes, but I'm going to make it easy for us. The double angle identity for sine that we developed was 2 sine A cosine A. And then I'm going to leave some space here because we have some more interesting work to do. And then I'm going to put the first cosine double angle identity that we came up with down here. And that was cosine squared A minus sine squared A. Right? So that's our first step, is to set these up. Now, to simplify this, we're going to do what we have done before, and that is we're going to set the lower left term in this fraction to 1. And I'll show you what I mean by that. Okay, so the lower left term is cosine squared A. So what we're going to do is divide everybody in the club by cosine squared A. That's here. Marker's trying out a little bit. And then it's here. Here's what I'm going to do. It's cosine squared A, right? But I'm going to divide it up between the two. Instead of writing it as squared, I'm going to write it as cosine of A twice, right? These are both squared. I'm dividing everything by a squared. And this is still dividing it by cosine squared A, but I'm just writing it separately. Does that make sense? That's the same thing. All right? Okay, now the magic happens. Are you ready? Now we go into simplify. This, I'm going to write it down. Let's see, I'm trying to think of the easiest way to do this. Let's start down here and simplify this first. This cancels out, and the lower left goes to 1. This, sine over cosine, is tangent. So we can write right here, tangent squared A. This is squared, so this is squared. Make sense? Now we go up here and we're going to simplify these separately. That's why I wanted to write the cosine not as a square, but I wanted to write each cosine of A separately so that I could cancel them against each of these numerator bits. So this is going to be, this will simplify. I've got 2 on the outside. Then I'll have tangent of A here. And then I'll have 1 right there. This cancels, right? I don't need it as a 1 because it's multiplying. So that cancels as well. So our final answer is that the tangent of 2A equals that. And let's see, I've been putting puffy clouds, haven't I, around them? Yes. So I'll do the same here. I wanted to put a square around it, but I'm going to stay true to what I was doing before. Okay, so again, tangent does not require a separate identity. We develop tangent by using the sine and cosine identities. And it's the first of the cosine because we have 3 to choose from. Makes sense-ish? I hope it makes sense, okay? So now we have developed all 3 double angle identities. Sine, there's 1 form. Let me just show you to remind you. There's 1 form for sine. There's 3 forms for cosine. And there's 1 form for tangent. Now we're going to turn our attention. That's not enough. That's not enough. Oh no, there's more. We're going to turn our attention to developing what we call half-angle identities. And let me show you what I mean by that. Let's just review what we've already figured out. We've done some identities, which we said were A plus B. And we did difference identities, which are like A minus B, right? We memorized these a couple weeks ago. We just figured out double angles, and we're calling those 2A, right? And we realized that we developed the double angles by referencing the sums, right? We change these and make them both A's, and that allows us to change it to a 2A. And now what we're going to do is we're going to develop what's called the half angles, which in some cases we'll use the expression x over 2, but we're going to say that x over 2 equals A. That's confusing. I'll come back to it. But these half angle identities, they're going to be derived from our double angle identities. So just like we relied on these to help us develop these, we're going to rely on these to help us develop these. All right? That's what I'm talking about, this way that we manipulate identities that we've already learned to create new ones. Now we're taking the new ones that we just learned and using them to develop more. So, to develop the half angle identity for sine, we're going to work on that one first. We need the second and the third forms of cosine. Oops, 2A. Not just A. Well, that's just a mess now, isn't it? 2A. All right, so what we have to do is we have to go back and develop that in our heads. I'm going to do it a little faster than I did it the first time, but the more times you do this development, the faster you should be able to go, the more you can carry it in your head. So let's start. We had cosine of A plus B, and this is what we had to memorize, right? Sine is the opposite. Okay, then we switched it and said, let's not have any B's. Let's call them both A's. So we can change that now. And now we can multiply these together because that's cool. And there we have it. There's our first form. Now we're going to take that little Pythagorean pup and slide him in here. We want to change this one first, right? We want to change cosine first because that's the one that's easier. It doesn't have the minus sign in front of it. So we take the Pythagorean form, right? And now we're going to substitute this in for that. So we'll get cosine of 2A equals 1 minus sine squared A, right? We're substituting this in for this, but then we have this other piece. So now we can put that together. Cosine of 2A equals 1 minus 2 sine squared A. There's our second form. Now we go back up here, and this time we're going to substitute in the fact that sine squared A equals 1 minus cosine squared A, right? We're using the flip side of this one. These are the Pythagorean dudes jumping into our problem. So now we put this in number 1, right? Sine squared, sine squared. This is where the minus sign gives us trouble. So I'm going to do the cosine of 2A equals cosine squared A minus, I'll write it all out this time. This is what goes into the parentheses, 1 minus cosine squared A. And then we'll distribute that to get the third and final form. I'm going to squish it down here because I want all my angles to be right here. 3, this is the final third form. It is 2 cosine squared A minus 1, because this becomes a minus, that becomes a plus. I take this one and I add it to that one. This is the final form. I did it faster this time, didn't I? But as you keep repeating this process, you will pick up speed and get faster and faster. As you can carry certain steps in your memory, go ahead and do that. Okay, that's the idea, is that you don't have to write out all of these steps every time. You can carry more and more of it in your head. Okay, so now what we're going to do is we're going to take the second form right here, and I'm going to copy that to the top of the next page. So this is the second form. I forgot to look at it. It's cosine 2A, it's 1 minus sine squared A. Okay, so that's the second form of cosine of 2A, just the way we developed it. Now what I'm going to do is I'm going to solve it for sine squared. Okay, so how am I going to do that? Let's see, I better swim that 1 over. Right? And then I'm going to divide it by minus 1. Okay, that's going to cancel that negative sign. Now, this is going to flip both of these signs, right? It's going to make the 1 go positive and it's going to make this go negative. So what I'm going to do is just change the order. I'll put the positive 1 first, and then I'll put the negative cosine of 2A second, just because that reads cleaner, right? And then this equals sine squared A. And now I'm going to take this, I want to get rid of this square, so I'm going to take the square root of both sides. All right, this is all falling under the overall step of solving for sine squared A. Actually, I want to solve it for we're going to solve it all the way down for the sine of A, okay? So we already got it down to sine squared A. Now I'm taking the root to get it to sine of A. This I'm going to pull over here. So I get sine of A equals plus or minus, because it's the root, of 1 minus the cosine of 2A, right? We're good, we're good, we're good. Now I'm going to do something that's going to blow your mind. We're just going to change the letter A to x over 2. What? Yeah, we're just going to change it. We're going to make it look different. So look what I'll have. I'll have the sine of x over 2 equals plus or minus square root of 1 minus cosine. Okay, here it gets a little crazy. 2 times x over 2. Right? I just substituted it in. And then I'm going to simplify one last step. This 2, which is technically over a 1, and this 2 will cancel. So my final identity is that the sine of x over 2 equals plus or minus the square root of 1 minus cosine of x. Wow. There, my friends, is our half angle identity for sine. Right? We derived it from the second form of the cosine double angle identity. We solved it for sine squared and then sine of a. We got that by itself. Then we did this really crazy thing where we just said, okay, we're taking the a's and we're turning them to x over 2's. And we're allowed to do that. I know, that seems like some sort of crazy voodoo, but we can. And this is the final version of this new half angle identity. Okay, now notice that used the second form of cosine double angle, and it allowed us to develop the sine half angle. Now we want to develop the cosine half angle. And guess which form we're going to use? Number 3. Just want to write, these are the steps. Okay, so let's go develop. This was the, I'm just going to write this here because I want to make sure you're remembering. This is the sine of x over 2. That's the sine half angle identity. Now we're going to develop the cosine. We're getting there. To develop the cosine half angle identity, we start with the third form of the cosine double angle. And this is the last part of our lesson, by the way. Okay, so let's see, we were way back here. We used the second one to get the sine half angle. Now we're using the third one to get the cosine half angle, right? Remember how I said to develop the half angles, we were going to use the double angles? Well, here we go. So cosine of 2a equals that. It's cosine 2a. Okay, that's what we developed back here. There it is, yay. And now the steps parallel. We're just doing cosine instead of sine. So here are our steps. We want to solve for cosine squared a, and then once we get that, we'll take it to cosine of a. Okay, so we have to I did something wrong last time. I did something very wrong in the last one. I'll fix it. I'll do this one correctly, and then I'll go back and fix the last one. I forgot this 2, right? There should be a 2 right there, and I forgot it, and I didn't do this right. So I'm going to go back and fix it. Okay, so this one I'll do correctly. We're solving it for cosine of a. There it is right there. So the first thing we want to do is add 1 to both sides. Right? And then we're going to divide both sides by 2. Right? These cancel. This I'm going to bring over to the other side. Cosine squared a equals Okay, this is all looking good. Then we take the square root, right? Because we're not looking for cosine squared. We want the square root of this. So we say that the cosine of A equals plus or minus cosine of 2A plus 1, and it's all over 2. And then we're going to swap our A's for x over 2. And then what that's going to do is say that the cosine of x over 2 equals plus or minus and what I'm going to do is I'm going to simplify this right away so we don't have to make a crazy complex fraction in here. 2a